Hello and welcome everyone on this Kubernetes Community Days conference. In the next 30 minutes, we are going to talk about model inferencing on Kubernetes with KServe. My name is Cseh. I am working as a lead software engineer, and here is my colleague and good friend, Gábor Lovass, who is working as a senior data engineer. We are both coming from Altair, or actually CMS, because CMS acquired our company. The deal was just closed some weeks ago, so this is official now. We are from CS. Quickly, the overview of the talk. We are going to talk about model serving in general. What are the challenges here? Why Kubernetes is a great platform for model serving. How KServe comes in. A little bit closer to the right topic. Okay, sure. Sorry. Okay, so let me continue. How KServe comes into the picture, how KServe helps in model serving, model deployment, and model inferencing. We will look at the model serving runtimes, the LLM serving runtime, and the different storage options in details. And at the end, we will show you KServe in action. But let me ask you first, who has heard about KServe? Okay, who are using KServe on a daily basis? Okay, cool. Okay, what is model serving? So model serving is an integral part of the machine learning lifecycle. If you think of that, data scientists are spending time creating, training, fine-tuning a model. It works well on a computer, it works well on a laptop, but how can I put it to production? How could I scale it and use it on production? What about large language models? So this is where model serving comes into play in the whole life cycle. So model serving is the process of deploying and making machine learning models available so it can handle inference requests and make predictions. Exposes trained models for APIs or services for application to receive predictions. So actually, it bridges the gap between model training and practical use in production. So I was talking about model serving. Let me switch to the model deployment part. So deploying a model as a microservice is the most common model serving strategy. This is where Kubernetes becomes relevant. So Kubernetes is a great platform. This is a container orchestration platform. It's designed for deploy microservices with resource management capabilities and load balancing. It provides reproducibility and portability with YAMLs in cloud-agnostic way. Provides horizontal scaling features for both CPU and GPU workloads. It's fault tolerance as well. Resilient outages and minimized downtimes. So these are the main points why Kubernetes is a great platform for serving models. On the previous slides, I was talking about the concept of model serving, a little bit about model deployment and why Kubernetes is a great platform. But if you think the idea of model serving, model deployment, and model inferencing is a very complex thing. I mean, on production, it's a very complex thing. We are living in an era where almost every month new services, new products are coming. Everything is changing very quickly. There are many model frameworks, model formats, for example. Not easy to handle and manage them and keep everything up to date. There are many challenges around LLMs as well. So there are many things which we have to take into consideration when we are talking about model serving, model deployment, and model inferencing. So it's very important to simplify how to serve your models on production. And here KServe comes into the picture. So what's KServe? Why KServe? In one sentence, it bridges the gap between the Kubernetes platform, the Kubernetes knowledge, and the model serving challenges I was talking before. It's a solution for many model runtimes you want to inference on top of Kubernetes like Huggingface, PyTorch, TensorFlow, Scikit-Learn. You know that Kubernetes was built to be a generic engine to enable you to build application platforms on top of that. KServe is similar to model serving and model inferencing perspective. So KServe is highly scalable, standards-based cloud-agnostic model inference platform. It's an open source project. The current version is 0.15.0, which was released 3 weeks ago. It provides a standardized inference protocol, supports serverless autoscaling, provides model inferencing, pre- and post-processing, monitoring, and explainability. So let's look at the core concept of KServe, which is serving runtime and inference service. Serving runtime defines the templates for pods that can serve one or more model format. So, serving runtime is for KServe admins. You need some Kubernetes knowledge, how to serve your models, specify the container image, the arguments, the environment variables. These are necessary to launch the inference service. Inference service allows to specify the model formats and version for a trained model. On the user side, the YAML is much more simpler. You need to specify the model format and the version if you want, and KServe will be able to auto-select and use the serving runtime to launch your model. But you can also specify the serving runtime if you would like to use a concrete one. So from a user perspective, you just have the inference service YAML, you deploy it, and once it's deployed, you can call and use your model. It's quite simple, right? So the goal of KServe to make the model serving and inferencing much simpler on Kubernetes. So I was talking a lot about serving runtimes. Here is the serving runtime support matrix with KServe 0.15.0. KServe supports a wide range of model serving runtimes, which supports a wide range of model formats. For example, at our company, with the help of KServe, we are able to support all model formats mentioned above. We are mainly using KServe based images, I would say, and KServe Triton serving runtime to cover almost every type of model formats, LLMs as well, but you can see that there are some overlaps here. I was talking about the core concept of KServe. Let me show you an inference service deployment in details. Right-hand side, you can see a YAML definition which contains transformer and predictor as well. Let's see what's the role of KServe here, what's happening here. So if you deploy this YAML, KServe controller understands the inference service custom resource. Based on the config we set, it could be raw deployment or serverless deployment with help of Knative. So we have the transformer service, we have the predictor service, we have pods for the transformer, we have pods for the predictor. The predictor, when it's initializing, it's using what we call storage initializer. Storage initializer responsible for load and copy the models from external storage to mounted MTD volume where the predictor can read the models from. So we deploy this YAML, we have the model loaded, the services pods are running. What happens when a user or an application makes a request? So on the top, we see the AI application, which sends the request to the transformer service. The transformer service makes the processing with the request and call the predictor service. Predictor makes the prediction and gives the prediction back to the transformer for post-processing. And the response goes back to the user or the application. On the previous slide, I was showing the storage initializer to you. Let me show you another option, which is great for serving LLMs, for example. So on the left-hand side, you can see the KServe traditional approach for model initialization. So if we have an Yeah, we have a storage initializer init container, which is responsible for copy and load the models from an external storage to a mounted MTD volume. This process is good for small models, but becomes a bottleneck for larger ones like LLMs, significantly delaying startup times in normal or auto-scaling scenarios. To overcome this problem, KServe introduced the model car feature you can see on the right-hand side. Model car operates as a sidecar container next to KServe container. This sidecar container holds the data where the model is encapsulated within an OCI image. So through Kubernetes feature of sharing process namespace, all containers within the same pod can read each other's file system. This ensures that the primary KServe container can access the model data directly from the sidecar without making redundant copies. At our company, we are using this model car approach for serving LLMs. So quickly about LLM serving runtime. KServe supports Huggingface LLM serving runtime out of the box with two backends, Huggingface and VLLM. And once again, model car, which I just showed you before on the previous slide, is used for serving LLMs mainly. We are also using it, and you will see in our demo. Okay, and with that, let me give the word to Gábor, who will show you two model inference examples with KServe.
Hello, everyone. Welcome. We have now arrived at the demo part of our presentation, and we would like to have a live demo for you. But also we have prepared with some video recordings just to frighten Mr. Murphy and his laws, and also to avoid the demo effects. So yeah, also a side note that at the end of the presentation, we will share a QR code with you that will point to a GitHub repository where you can find this presentation and also every file to reproduce what we will do during the following 15-ish minutes. Okay, during this demo, we are going to solve a complex yet very useful and important task, I think, with the KServe inference service. And in general, we will simplify the issue a lot to get into this demo, but we will go through the solution step by step. And in the end, we will deploy an inference service and test it. Okay, so let's get to the details. So the issue we would like to solve is that we would like to detect errors in a Kubernetes cluster as soon as possible to avoid outages and to prevent users facing issues in our software. So basically, we want to create an alerting application that detects anomalies in a log or in logs. From the logs themselves, we have to know that it is collected by another subsystem. We don't need to know anything else, just the fact that the logs will be collected and it will periodically call our inference service to determine if the logs are healthy or not. Okay, so for anomaly detection, we will use a one-class support vector machine algorithm that is an easy unsupervised learning machine algorithm. It basically just learns decision boundaries that encloses the majority of the data points, and it considers everything anomaly that is outside of this boundary. On the GitHub repository, we will have a simple Python script that will generate some considered to be normal log statements, and we'll train a support vector machine model. And from precision point of view, you have to know that with the generated data, it won't perform magic. But from KServe point of view and from the point of this demo, it will do the job. It's easy to train, it's easy to test, and we will see some results. Okay, after we have the model, we will upload it to storage. It can be a S3 bucket or some Google Drive storage, or in our case, we will just simply push it to the GitHub repository, so you will also be able to use it later for testing. Okay, after these steps, we can create an inference YAML, and we will try to deploy it to our production-like cluster, and then try to infer with this inference service. Yeah. Okay. So let's jump the demo part. So here you can see there is a train detector Python script that you can check. Whoever is interested in details just really need to know that it can train the support vector machine model, and basically that's it. What is more interesting from our conference point of view is the deployment descriptor or inference service descriptor YAML. First, I will just simply apply this YAML for you, and until it gets healthy in the background, we can see what's going on there. Okay, so is it visible? Yeah, okay. You can see that we can attach annotations and labels to our inference service, but what's more interesting is the predictor itself. The predictor itself is a Kubernetes type podspec object, so we can do a lot of interesting things here. For example, we can define the mtdir volume, as Peter mentioned before, and also we can define init containers. For example, the storage initializer that is responsible for downloading a specified model to this mtdir volume. Here in the args section, you can see that we will use the model we just pushed to our GitHub repository, and also we can define the path where we would like the storage initializer to download the model. Okay. Otherwise, just some resource settings, and also it's important not to forget to add the volume mount to the container. Yeah, in the container section, we can define the main container that will do the job for us. As you can see, we use the Scikit-Learn server runtime for inferring, and in the argumentum section, we can define the model name. We can define the path where the model is located at, and also the port where the inference server will listen on. Okay, so hopefully it got healthy. So let's check the inference service. Yeah, it's considered to be true. As Peter mentioned, we can check that the KServe actually really created a service for us, and if we check the pods, there should be an anomaly detector pod created for us, and it's in running state. Okay, so let's try to test it. First, let me show you an inference input. Here, as you can see, there are no logs or log messages in this JSON. That's because we had to manually convert the log messages to their feature vector representations. So basically that's the inference input, and here we provide a simple curl command where we use our production client cluster for this demo. It's really identical to our production cluster, just it's for us developers. So if we just simply try to do an infer and kind of format the response, we can see here that the first log message was considered to be normal, and the second one was considered to be an anomaly. Yeah, it's not the best that you have to infer with the feature vectors itself. So to avoid this, and to avoid the scenario where other applications need to know how to transform a log message into a feature vector, we can add a transformer to our inference service. For that, we provide you a simple transformer script. Basically, we just define a transformer class that extends the KServe model class, and here you can define pre-process steps and post-process steps. You just need to know that that's how KServe suggests to do it, and basically it will really transform the pure string log messages into feature vectors. Also, we provide a simple Docker file for you, so you can build a transformer for yourself if you wish. And yeah, that's it. Let's see how the YAML changes. But first, let me apply it again, just to make sure it gets healthy until I show the details. All right. So basically, it's really similar to the previous YAML I showed you. It's actually the same until line 42, because we modified the listening port from 8080 to 8085 for the predictor container. And as Cseh mentioned already, or Peter mentioned already, you can define transformers on the predictor level. So you could define it here. In this scenario, KServe would handle it as a separate deployment, which has its advantages like independent scaling if needed. But for this demo, we just simply encapsulated it to the predictor. We can define a transformer container. We can use the custom transformer image we can create with the Docker file and push to the registry. And here it's gonna be the main container listening on port 8080, and we have to define the predictor host to localhost 8085 just to make sure the communication will be okay. All right, so hopefully everything got into a running state in the background. Yeah, perfect. So let's see how an inference input can look like now. As you can see, now there are actual log messages we can send to the inference request. The transformer will create feature vector representation, and on the prediction results, it will do some transformation again for us. So let's see how it works. So if I hit infer, yeah, so you can see now that the first log message can be considered to be normal, as it's just a simple statement E, and the second log message can be considered to be an anomaly, as it is a critical issue. Okay, so to sum up, we have kind of solved this issue, what we really simplified for this demo. And let's get back to the second one. All right, as Peter already mentioned, large language models, we wanted to do something with them as well. So due to the rise of the large language models, there have been attempts to use them for anomaly detection. So let's say we would like to improve our previous solution to use a large language model. Choosing a large language model for anomaly detection can be effective if we consider the fact that it can understand and model complex patterns and semantics in natural language logs, and also it can generalize between different system logs in the format of them. Also, additionally, they can be fine-tuned on domain-specific log patterns. So if you have a huge collection of logs, you can make the performance of a large language model quite good, I think, with it. You just have to put the effort there to fine-tune it. Yeah, for this demo, first we will download a large language model. After that, we will skip the fine-tuning part, as that would take too much time to show. But with some prompt engineering, we will hack the system. And yeah, basically, we will download the QAM model. We selected the QAM model because it provides some lightweight large language models that can perform quite well. Yeah. And after, let's say, we fine-tuned our model, we can package it to an OCI image and use it as a model car approach just to test the other storage option already mentioned by Peter. Okay, just to take a look at in the details.
Yeah.
Here is a simple Python script that will download a large language model from Huggingface for you. It's really nothing difficult. Here is the QAM model I already mentioned we selected for this demo, and it will download the model around 3 GB of the size to a model folder. Then we also provide the Docker file for you, which basically just simply copies the content of the model to itself. And then we can check the YAML. It's again a similar YAML to the previous ones. What is important here that for now we use the Huggingface server runtime for loading the large language model. Also, we had to attach an NVIDIA GPU to it to be able to properly load the shards. And here is the new thing, the model car. As you could see, there was no init containers, there was no storage initializer, as we use the model car approach now. So here is the model car. We can define a simple image. We just, let's say, push the registry.
Goodness.
And basically, that's it. Here, I just set some affinity selector for node selector just to make sure we get a GPU for ourselves. All right, I know I haven't applied this YAML just because I did it previously just to make sure we get a NVIDIA GPU in time for this demo. So let's check how the input looks like. So first, you can see a system message for the large language model that, hey, you are a log anomaly detector. If the log contains keywords of error, critical, just mark it as anomaly. Otherwise, you can consider it to be normal. And the second message can be considered as a user message, like a simple critical log message. So let's see it in action. And fingers crossed that the last demo call will work as expected. Great. Let's do the infer. And here it is. It was considered to be an anomaly, and the log message was a critical issue. So I think we saw the issue again. And that was it from my end, from the demo part, I think. And yeah, just to sum up, we solved this log anomaly detection issue with the KServe inference service in 2 different ways. I think we proved it. So yeah, thank you very much. And there is the promised QR code.